In our next section of Chapter 12, we're going to look at polar coordinates, and you may recall these from your trigonometry class before. And so if you still have some of those notes or your books, you might want to go back and do some review of polar coordinates and polar systems from trigonometry, or maybe even watch just a quick Khan Academy video that might help you get better set up for this chapter. So suppose you work for a company that designs heat shields for space vehicles. The shields are thin plates that are either rectangular or circular in shape. To solve the heat transfer equations for these two shields, you must choose a coordinate system that best fits the geometry of the problem. A Cartesian rectangular coordinate system is a natural choice for the rectangular shields. However, it doesn't provide a good fit for the circular shields. In this case, a polar coordinate system in which the coordinates are constant on circles and rays is better suited for the circular shields. Like Cartesian coordinates, polar coordinates are used to locate planes, or points in the plane, I should say. When working in polar coordinates, the origin of the coordinate system is also called the pole. And the positive x-axis is the polar x-axis, the polar axis. The polar coordinates for a point P have the form r theta. The radial coordinate r describes the signed or directed distance from the origin to P. The angular coordinate theta describes an angle whose initial side is the positive x-axis and whose terminal side lies on the ray passing through the origin in P. Positive angles are measured counterclockwise from the positive x-axis. Again, a good review from trigonometry. With polar coordinates, points have more than one representation for two reasons. First, angles are determined up to multiples of 2 pi radians. So the coordinates r theta and r theta plus or minus 2 pi theta refer to the same point. So you can see here we have, this is r theta, but it's also r theta plus 2 pi or minus 2 pi. The points r theta and negative r theta and negative r theta are reflections of each other through the origin, which you see here. This means that r theta, negative r theta plus pi, and negative r theta minus pi all refer to the same point. So if we have negative r plus pi, we're going clockwise, and we end up here. If we have negative r theta and we subtract pi, we're going the counterclockwise direction the same way, halfway around the circle. The origin is specified as 0 theta in polar coordinates, where theta is any angle. Let's look at example 1 based upon what we've just learned about polar coordinates. Graph the following points in polar coordinates: Q, which is 1, 5 pi over 4, R, -1, 7 pi over 4, and S, 2, -3 pi over 2. Also give two alternative representations for each point. The first point, Q, 1, 5 pi over 4, is 1 unit from the origin on a line OQ that makes an angle of 5 over 4 5 pi over 4, 5/4 pi. Remember, pi is 180 degrees, and so we're going 1/4 of that further. So another 45 degrees, if you will. This is 1 unit from the origin O on the line OQ, which you can just see here. And it's going along the positive x-axis because it's a positive value. Subtracting 2 pi from the angle, Q can be represented as 1 -3/4 pi. That's coming this direction. Since we had 1 1/4 pi and the whole revolution is 2 pi, this would be -3/4 pi. Simply subtracting pi from the angle and negating the radial coordinate, we get, if it's subtracting pi from the angle, takes us back 180 degrees to the first quadrant, or pi over 4. But then it changes the sign of the radial element from positive 1 to negative 1. Remember, when they're in opposite directions on a straight line, the radial component are opposite signs. To locate the point r, negative 1, 7 pi over 4, it's easiest first to find the point r, 1, 7 pi over 4. Well, 7 pi over 4 is almost completely around, right? It's almost 2 pi. So it's 1 3/4 pi. So we're down here. And then to find the negative 1, we would just subtract pi from that, okay? So it's actually in the second quadrant. So this negative 1, 7 pi over 4 is the reflection of r star through the origin. And there you can see r star there. I'm sorry those are a little bit small. I'll try to make them bigger. Okay, other representations include negative 1, negative pi over 4 by simply adding pi to that, or subtracting pi from that, and 1, 3 pi over 4. And that's going around. That's the original one we just saw. Nope, that's adding 2 pi to our original equation, or coordinates, I should say. The point S, 2, negative 3 pi over 2, this is a pi and a half, and it's negative, so we're going to go in the reverse direction, and so we end up at basically the 90-degree angle, or pi over 2. Again, because it's negative, we go clockwise, and again, you should hopefully remember this from trig, or should go back and do a little review of trig and polar coordinates. The point can also be represented as 2 pi over 2, that's just adding 2 pi to it, or negative 2, negative pi over 2, which is adding pi, I guess it's subtracting pi and changing the sign of the radial coordinate. We often need to convert between Cartesian and polar coordinates. The conversion equations emerge when we look at a right triangle, in which the cosine of theta equals x over r, adjacent over hypotenuse, and the sine of theta equals y over r, or opposite over hypotenuse. Again, all of these are reviewed from trigonometry, in which you should have handled or become a little bit familiar with polar coordinates. Given a point with polar coordinates r theta, we see that its Cartesian coordinates are x equals r cosine theta and y equals r sine theta. Conversely, given a point with Cartesian coordinates xy, its radial polar coordinate satisfies r squared equals x squared plus y squared, and the coordinate theta is determined using the relationship that the tangent of theta equals y over x. Again, tangent theta equals opposite over adjacent, or y over x. All of these are, again, reviewed from trigonometry, or base knowledge you should have got in trigonometry. And as with these, the quadrant in which theta lies is determined by the signs of x and y. Figure 1221 illustrates the conversion formulas for a point P in the first quadrant, whether you're coming from xy or r theta. The same relationships hold if P is in any of the other 3 quadrants. And here we have again, just a restatement of this, kind of in a analytical or procedural way. A point with polar coordinates r theta has Cartesian coordinates x equals r cosine theta and y equals sine theta. This is now the 3rd time I'm saying it. And a point with Cartesian coordinates xy has polar coordinates r theta, where r squared equals x squared plus y squared, and tangent theta equals y over x. So make sure these are in your notes. Again, you might want to do a little brush up of review of trig. So this is a pretty simple example. I highly recommend that you hit pause and do these conversions, specifically just converting from polar coordinates to Cartesian and vice versa. For point A, or question A, part A, express the point with polar coordinates p equals 2, 3 pi over 4. Okay. If you look at the diagram here, we have the length of here is 2, and here we have 3 pi over 4, the angle, so 3/4 pi. Notice that x equals r cosine theta, which is 2 times the cosine of 3 pi over 4, which is negative square root of 2, and which makes sense because, and it should be negative here, and I don't see a negative. We know that the x-axis, or the values of x to the left of the y-axis, are negative, and y equals r sine theta, which equals 2 sine 3 pi over 4, which is the square root of 2. Again, what you may notice is what's left here is the reference angle. 3 pi over 4 is an angle whose reference angle is 45 degrees, and this is the 45, 45, 90 triangle. Okay, with the hypotenuse of 2. For part B, we're given Cartesian coordinates, and now we have to define them in terms of polar coordinates. Here we can see negative, or 1, and negative 1 down here. It's best to locate this point first to be sure that the angle theta is chosen correctly, as best shown in figure 1222 to the right. The point Q1, negative 1 is in the fourth quadrant at a distance of r, equals the square root of 1 squared plus negative 1 squared, which equals the square root of 2, which you can see here marked on the graph. The coordinates theta satisfies the equation tangent theta equals y over x, which is negative 1, 1. The angle in the fourth quarter, for which tangent theta equals negative 1, is theta equals negative pi over 4, or stated in a positive way, 7 pi over 4. Okay? Therefore, two of the infinitely many polar representations of Q are square root of 2, negative pi over 4, if we measure in the clockwise direction, and square root of 2, 7 pi over 4, if we measure positive 7 pi over 4, if we measure in the positive direction. Next, we're going to take a look at some basic curves in polar coordinates. A curve in polar coordinates is the set of points that satisfy an equation in r and theta. Just like in Cartesian, it's an equation in x and y. Some sets of points are easier to describe in polar coordinates than in Cartesian coordinates. We're going to begin by examining equations of circles, lines, and spirals. The polar equation r equals 3 is satisfied the set of points whose distance from the origin is 3. The angle theta is arbitrary because it is not specified by the equation. So the graph of r equals 3 is the circle of radius 3 centered at the origin. In general, the equation r equals a describes a circle of radius absolute value of a centered at the origin, as you can see in this green graph to the right. This might be similar to when we say x equals 2. A lot of students make the mistake of thinking of the point 2, 0. But x equals 2 is a vertical line all the way from positive infinity to negative infinity on y, because the y coordinates can be anything. The equation theta equals pi over 3 is satisfied by the points whose angle with respect to the x-axis is pi over 3. Because r is unspecified, it is arbitrary and can be positive or negative. Therefore, pi over 3 describes the line through the origin, making an angle of pi over 3 with the positive axis, as you can see here in this orangish color graph to the right. More generally, theta equals theta sub 0, or some constant, describes the line through the origin making an angle of theta sub 0 with the positive x-axis. The simplest polar equation that involves both r and theta is r equals theta. Restricting theta to the intervals theta is greater than or equal to 0, we see that as theta increases, r increases. Therefore, as theta increases, the points on the curve move away from the origin as they circle the origin in a counterclockwise direction, generating a spiral. So what's happening here is we keep moving around. We go from a measure of 0 for theta and 0 for r all the way around to 2 pi for theta and 2 pi for r. Let's look at a conversion from polar to Cartesian and see what happens with the graph and what shape it creates. Example 3, convert the polar equation r equals 10 cosine theta plus 24 sine theta to Cartesian coordinates and describe the corresponding graph. If we multiply both sides of the equation by r, produces the equation r squared equals 10r cosine theta plus 24r sine theta. Using the conversion relations that r squared equals x squared plus y squared, and the fact that x equals r cosine theta, which you can see here, and y equals r sine theta, which we can see here, notice that we can convert r squared into x squared plus y squared. We can convert this first term on the right to 10x, and the second term to 24y. So we've effectively eliminated the polar coordinates or polar variables and replaced them with x and y variables, which are Cartesian variables. If we rewrite this, so we have x squared minus 10x plus y squared minus 24y, and then we complete the squares both for x and y, notice what we get is x squared minus 10x plus 25, which is x minus 5 squared. And remember, you have to, when we add 25 in there, we have to subtract 25. That's how we're completing the square, so we're not changing the value. Here we get y squared minus 24y plus 144. 12 squared is 144. And so again, when we add 144, we have to subtract it. This is completing the square process from algebra, which may take you back a little bit. And so we get x minus 5 squared plus y minus 12 squared equals, if we play both the 144 and the 25 over to the other side, 169. Well, 169 is 13 squared. So what we have here is x minus 5 squared plus y minus 12 squared equals 13 squared. Well, this is the equation of the circle of radius 13, centered at 5, 12. And this is the standard definition for the equation of a circle that's centered at a point other than the origin. This is the standard equation, x minus x0 squared plus y minus y0 squared. And if it actually works for the origin too, because if x0 and y0 are zeros, then we just get x squared plus y squared equals the radius squared. While this presentation isn't quite as long as the last one, it's still a good 40 minutes, so we're about halfway through. This is a good point to take a break, get a coffee, take a walk, meditate, do a cartwheel, or break dance, which is normally what I'm doing between takes of these videos. Calculations similar to those in example 3 that we just did lead to the following equations of circles in polar coordinates. The equation r equals a describes a circle of radius a centered at the origin. And the equation r equals 2a cosine theta plus 2b sine theta describes a circle of radius the square root of a squared plus b squared centered at AB. Equations in polar coordinates often describe curves that are difficult to represent in Cartesian coordinates. Partly for this reason, curve sketching methods for polar coordinates differ from those used for curves in Cartesian coordinates. Conceptually, the easiest graphing method is to choose several values of theta and then calculate the corresponding r values and tabulate the coordinates. The points are then plotted and connected with a smooth curve. This isn't that much difference, typically we have equations defined, f of x or y is defined in terms of x, so we pick several values of x and then calculate values of y, which we then connect with generally unbroken lines or curves. Graph the polar equation r equals f of theta equals 1 plus sine theta. So what we're going to do here, notice the domain of f consists of all real values of theta. However, the complete curve is generated by letting theta vary over any interval of length 2 pi. Table 12.3 shows several r theta pairs which are plotted in figure 1226, which is down below as well. The resulting curve, called a cardioid, is symmetric around the y-axis. Plotting polar curves point by point is time-consuming and important details may not be revealed. As you saw in that last diagram, it has an unusual shape. Here is an alternative procedure for graphing polar curves that is usually quicker and more reliable. Procedure for Cartesian to polar method for graphing r equals f of theta. Graph r equals f of theta as if r and theta were Cartesian coordinates with theta on the horizontal axis and r on the vertical axis. Be sure to choose an interval for theta on which the entire polar curve is produced. Use the Cartesian graph that you created in step 1 as a guide to sketch the points r theta on the final polar curve. Let's look at an example because that's not really clear exactly how to do this, so hopefully the example will clarify. Plotting polar graphs. Use the Cartesian to polar method to graph the polar equation r equals 1 sine theta from example 4. Remember, now we're going to first graph it as if r is equal to the y value and theta is the x value. Viewing r and theta as Cartesian coordinates, the graph of r equals 1 plus sine theta on the interval 0, 2 pi is the standard sine curve with amplitude 1 that you see in the dashed line below. But it's also, this is shifted up by 1 because it's 1 plus sine theta, so we get this graph here that you see on the second graph to the right, r equals 1 plus sine theta. If we then convert each of these measures to angular measures and use the r measure as we go along, notice that the graph begins with r equals 1 at theta equals 0 and increases to r equals 2 at theta equals pi over 2. It then decreases to r equals 0 at 3 pi over 2, which indicates an intersection with the origin on the polar graph, and then increases to r equals 1 at theta equals 2 pi. The second row of these graphs down here on the bottom to the right show the final polar curve, a cardioid, as it's transferred from the Cartesian curve here. Obviously, there's some question about how do we make these smooth curves and what are the values in between, and you may have to find some, like finding the value of pi plus another fourth of pi, 5 pi over 4 or something. Given a polar equation in r and theta, 3 types of symmetry are easy to spot. First is symmetry around the x-axis occurs if r theta is on the graph whenever r negative theta is on the graph. And you can see an example here in the first graph below. And you can easily see that y becomes effectively the mirror with images above and below reflective or symmetrical to each other. Symmetry around the y-axis occurs if the point r theta is on the graph whenever r pi minus theta is the same as negative r theta. And so r theta is the same as r pi minus theta, or negative r negative theta. Okay, here we have kind of the negative theta as the reference angle there. Okay, and then finally, symmetry around the origin occurs if the point r theta is on the graph whenever negative r theta equals r times theta or r theta plus pi. And so we can see our r theta here. Well, pi is 180 degrees around. And here we have r theta plus pi, which is the same as negative r theta. Okay. Symmetry around the origin, I think, is sometimes the hardest to spot because it's symmetrical around the axis y equals x, the diagonal across a Cartesian system. For instance, consider the polar equation r equals 1 plus sine x that we just saw in example 5. If r theta satisfies the equation, then r pi minus theta also satisfies the equation because sine theta is equal to sine of pi minus theta. Therefore, the graph is symmetrical about the y-axis as shown in figure 128 that we saw, 1228, which is the one we're looking at right here. Testing for symmetry produces a more accurate graph and often simplifies the tasks of polar equations. So let's look at an example of plotting a polar graph. Graph the polar equation r equals 3 sine theta. The Cartesian graph of 3 sine 2 theta, on the interval 0 to pi has an amplitude of 3 and a period of pi. Remember, this is the period coefficient here. So we get 2 pi over 2, which gives us a period of pi. We can see that on the left, it's basically the sine curve moving through its whole period in pi, and then so we've got two whole representations. In order to get through all the way through to 2 pi, we have to do 2 period iterations here. We can see that at 0, at pi over 2, at pi, 3 pi over 2, and 2 pi, we have origin intercepts, that the value of r at those points is 0. Okay? So those theta intercepts, just like x-intercepts, occur at theta equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. These correspond to the intersections with the origin on the polar graph. Furthermore, the arches of the Cartesian curve between the intercepts corresponds to loops in the polar curve. The resulting curve is a 4-leaf rose that you see in the graph down here on the right. The graph is actually symmetrical around the x-axis, which you can see, a mirror. It's symmetrical around the y-axis, and it's also symmetrical around the origin. It is instructive to see how these symmetries are justified. To prove symmetry around the y-axis, notice that r theta on the graph, r equals 3 sine theta, r equals negative 3 times the sine of 2 times negative theta, negative r equals 3 sine 2 negative theta, which gives us negative r negative theta on the graph. We see that if r theta is on the graph, then negative r theta is also on the graph, which implied this symmetry around the y-axis. Similarly, to prove symmetry around the origin, notice that r theta on the graph implies r equals 3 sine 2 theta. Well, this is r equals 3 sine 2 theta plus 2 pi, a coterminal angle. Therefore, r equals 3 sine 2 times the quantity of theta plus pi, which gives us r equals theta plus, gives us the coordinate r, comma, theta plus pi. We have shown that r theta is on the graph, and if r theta plus pi is also on the graph, this implies symmetry around the origin. Symmetry around y and the origin implies symmetry around x. Had we proved these symmetries in advance, we could have graphed the curve only in the first quadrant. Reflections around x and y axis would produce the full curve. Now let's look at another example. Graph the polar equation r squared equals 9 times the cosine of theta. The graph of this equation has symmetry around the origin due to the r squared and about the x-axis because of the cosine theta. Cosine is the same on each side of the x-axis, some opposite values on each side of the x-axis, These two symmetries implied symmetry around the y-axis. A preliminary step is required before using the Cartesian dipolar method for graphing the curve. Specifically solving the equation for r, we find that r equals plus or minus 3 times the cosine of theta. Notice that the cosine of theta is less than 0 for pi over 2, for theta between pi over 2 and 3 pi over 2, or 90 and 270. So the curve does not exist on that interval. Therefore, we plot the curve on the intervals theta is between 0 and pi over 2, and theta is between 3 pi over 2 and 2 pi. Thus, the interval negative pi over 2 and pi over 2 would work so that we have a consistent figure all the way around. Both the positive and negative values of r included are in the Cartesian graph. Okay, so we can see here that from pi over 2 to 3 pi over 2, where cosine or the x values are negative in this model, we have no values. So if we just basically shift this again and notice that it's 0 at pi over 2 and also at 3 pi over 2, we can draw this graph, and here, pi is that goes on the r value between 0 and, negative 3 and 3. We then have the graph here to the right. Now we are ready to transfer the points from the Cartesian graph to the final polar graph, and this is called a lemniscat, this curve here. So when we plotted the points, we had no values here between between pi over 2 and 3 pi over 2 because of the way we solved the equation. We cannot take a value of cosine in quadrants 2 and quadrants 3. So notice, so that was one thing. The first part of this that's, I think, challenging is recognizing we need to solve this because we're plotting r against theta. The second part is recognizing these values are blank, and so trying to figure out how do you do that when you go around the curve. And so instead of plotting from 0 to 2 pi, again, we went from, we plotted from, I went just from blank, from negative pi over 2 to pi over 2. Let's look at our next example, matching polar and Cartesian graphs. The butterfly curve is described by the equation r equals e raised to the power sine theta minus 2 cosine 4 theta for theta between 0 and 2 pi. Here we see it plotted in the Cartesian coordinates and in the polar coordinates. Follow the Cartesian graphs through the points A, B, and C all the way to N and mark the corresponding points on the polar graph. Okay. Well, notice the point A in 1231 is r equals negative 1 and theta equals 0. Okay, so we get negative 1, 0. This is marked as A on this other plot as well, because remember, x equals r cosine theta, and the cosine of 0 is 1, so we get negative 1, and then y is r sine theta, and sine theta is 0, so we get negative 1, 0 there. And that's our point A. Point B is on the Cartesian axis, which means that r is 0. So in this case, both x and y are 0 because you have r sine theta and r cosine theta. So point B is at the origin, which you really can't see here in the polar coordinate. Okay? The same argument used to locate B applies to F, H, J, L, and N. These are all theta intercepts, which means that r is 0 for them, so x and y are both going to be 0 too. So these are points where the graph comes back to the origin. And then the other points, C, D, E, G, I, K, M, and O, these kind of correspond to I just went blank there, sorry, correspond to the extreme points of the loops. So you can see that C and E are roughly the same size. D is this little loop in there. Then we get loop, I don't even see, oh, we got D, and then we have G over here. D's this little loop. A makes a loop. I is this loop here. K is this loop here. And M is this loop here. So you can see this is, while it's maybe simpler to graph the Cartesian system, then kind of relating it back to the polar system can be very challenging. And again, one of the key information pieces are the theta intercepts, where r is 0, so x and y will be 0. So everywhere the polar graph is 0, then we're back at the origin for the actual polar graph, the polar Cartesian model, I should say, and then converting it to the polar graph. All right. This is the Cartesian graph with r as y and theta as x. You can see that when graphing polar curves that eventually close on themselves, it's useful to specify an interval in theta that generates the entire curve. In some cases, this problem is a challenge in and of itself. And so given that, this is a curious example. Consider the closed curve described by r equals cosine 2 theta over phi. Give an interval in theta that generates the entire curve, and then graph the curve. Recall that cosine theta has a period of 2 pi. Therefore, cosine 2 theta over 5 completes one cycle when 2 theta over 5 varies from 0 to 2 pi, or when theta varies from 0 to 5 pi. Therefore, it's really tempting to conclude that the complete curve, r equals cosine 2 theta over 5, is generated as theta varies from 0 to 5 pi, that is in fact our period. But you can check that the point corresponding to theta equals 0 is not the point corresponding to theta equals 5 pi. So this is a little bit confusing, which means that the curve doesn't end at the same part it starts at, so that can't be our period. And here we have a graph that shows what we would think would be the period, but we can see that it doesn't end and start at the same point. Okay? To graph the complete curve, r equals cosine 2 theta over 5, we must find an interval 0 to p, p being the period, where p is an integer multiple of 5 pi, so that the y value, or the value of r, I'm sorry, in this case y value because we're doing polar coordinates, is equal to f of p. That, that's what the definition of a period is you come back to the same value and then you start repeating the pattern. It also has to have an integer multiple of 2 pi so that the points a f of 0 and p f of p are the same, okay? Because cosine is 2 pi. The smallest number satisfying these conditions is 10 pi. Graphing r equals 2 theta over 5 over the interval from 0 to 10 pi completes the complete graph, which looks drastically different. You can see the sections of the white graph above when we just graph from 0 to 5 pi, but a whole part of the graph is left out of this. So it's quite curious and quite interesting. And most of us will not be graphing shapes like that. We'll be using computers and graphing utilities.